So thanks for turning out today on a nice, warm, sunny afternoon to come hear about quantum mechanics. Hopefully it will be worth your time. So I'm Eleanor Twyford. I work in theoretical quantum optics, which is about the interaction of quantum light with matter, broadly speaking. But my particular area of interest is in this theory as it applies to engineered quantum devices. So rather than natural atoms, these are things like superconducting circuits, which behave like artificial atoms. So I'm going to take you briefly through today the kind of general idea of quantum mechanics and try to explain how some of the weirdness of quantum mechanics, which you're probably quite familiar with, actually comes about as a consequence of the mathematics of quantum mechanics. And then we'll talk through a little bit about how we start bringing that weirdness of quantum physics into the everyday realm that we're used to. So to start, we're going to try a bit of an experiment and do just a little bit of a poll to see what you think of when you think of quantum mechanics. So you can scan this QR code with your phone, or you can go to the website vvox.app and enter this code. And if you can maybe give us a thumbs up in the Q&A once you've done it, I'll give you a couple of minutes. It's great to see a lot of jokes coming in about quantum physics today. I may have to steal some of those to torture my second-year undergraduate students with. I teach the second-year quantum physics course here at Southampton. Okay, let's carry on and see if this works. So we'll open the poll now. And it's a very simple question. Just type a couple of words or a phrase. What do you think of when you hear the words quantum physics? What are your associations with quantum mechanics? You can type more than one word as well if you want to. More than one answer is fine. I should have stashed some jokes up my sleeve to do while you're answering this poll. It's quite an interesting one, quantum physics, because I think more than really nearly any other theory of physics or any other aspect of physics, it's very much captured kind of popular imagination, and it's ubiquitous throughout a lot of our culture, through science fiction, through television, through books and movies, through kind of even just our popular language. I think it's a sign of how exciting it is, even if you don't know all of the mathematics. It's such an interesting and counterintuitive theory. Okay, it looks like the answers are slowing down now. So let's take a look and see what we've got here. Ah, excellent. So particles, we have a lot of particles in here. There's some wave functions. We've got Schrodinger's cat. I was hoping cats were going to be bigger in here. Wave particle duality, ridiculous, absolutely. Small, really small, very, very, very small. Double slit, electrons, spooky action is in there, quantum computers, other universes, paradoxical superposition, excellent. So we'll talk about a lot of these things today, and hopefully it will be interesting. Thanks for that. So let's carry on and look very briefly at the difference between particles and waves in classical mechanics. And you may not understand all of these equations yet. That's okay, don't worry about it. Particles, we understand particles pretty intuitively, don't we? Particles are like billiard balls, for instance. They are localized in space. We can calculate their position as a function of time. We call that a trajectory. And we can calculate the position as a function of time. We can calculate the velocity as a function of time. And there's an equation of motion, which comes from Newton's laws, which describes how that position of the particle changes in time. And any variables that we care to think about, things like velocity, momentum, energy, position, all of these things are fully determined for all times. Once we know what the potential is or the force, and we know what the initial conditions are or the conditions at some point in time, then for all other times, we can predict the values of those properties, those dynamical variables. In classical physics, we also have waves, and waves are a very different thing from particles. They occur in some kind of extended systems or some kind of medium. They could be water waves, they could be waves on a string, they could be electromagnetic waves. And these waves are described by a wave function, which tells you what the amplitude of that wave is at any position in space and any time. And these wave functions are determined by solving something called the wave equation. And once you do that, we know all of the properties of the wave. We know its amplitude, we know its energy, we know its position. And so those wave properties at any point in space or time are now fully determined. So waves are different from particles, but in both cases, we can describe them by an equation that tells us exactly what they're going to do at any point in space and time. So you are probably familiar with, by now, double slit experiments. So let's think about first what would happen if we have particles. So we've got some beam of particles. Maybe think about them as paintballs. And then we've got a piece of plywood with two holes in it. And we're shooting paintballs toward these two holes. If you close off one of those holes, say one, then you're going to find paintballs over here at some later point. You'll see most of the paintballs sort of around the center of that slit, but then if they're coming in at different angles, you'll get some spread of those paintball splats that kind of broadly follows this distribution. And if we have slit 2 closed instead, then we see the same thing coming from slit 1, except that it's just shifted in position. Then if we have both those holes open at once, we would expect to get just the sum of those two distributions. So the overall distribution of the paintball splats would look something like this curve. So the intensity with both slits open is just the sum of the intensities with either one of them open. So what if we do the same thing with waves? So you could have some kind of wave front coming in that goes through slit 1 and slit 2, diffracts through those slits. If you have only one of them open, then again, you're going to find this kind of smooth distribution with a peak near the slit. Likewise with slit 2. So that's all similar to what we saw with the particles. But if we have both slits open, then what we find is not the same thing as we had with particles, because those waves can interfere with each other. And so you get this characteristic interference pattern, which has peaks and dips where it's actually equal to 0. So the intensity, if we have both slits open, is not the same as the sum with having one or the other open. So we get interference in this case. And that's a very characteristic property of waves. This is one of the experiments that really proved the wave nature of light back in the Victorian era, where there'd been some debate about whether light was a particle or a wave over a long time. And this is one of the experiments that seemed to fundamentally prove that light was a wave rather than a particle. But then it all got a little bit muddled up. And it turns out that some very clever experimentalists have actually gone and done this experiment with electrons. So if you have only one slit or the other open, when you're firing electrons from this electron gun, you get first an intensity pattern that looks like this for slit 1 being open, or an intensity pattern that looks like this if slit 2 is open. So that all looks as normal as we would expect particles. But then if we open both slits at the same time, what you find is this interference pattern. And you can see here that it's got kind of peaks and dips in it. If you take the cross section of it, it looks like this pattern here. So actually, we find that electrons, which we ordinarily tend to think about as particles, actually exhibit an interference pattern in a double slit experiment that looks characteristic of waves. This was actually discussed by Richard Feynman back in the 1960s. There's a footnote in the book that says, oh, well, you'd never actually do this experiment because you'd have to make it impossibly small. Which just goes to show that you should never tell an experimentalist that they can't do something unless you really want them to go and do it. So, in fact, it was only about 10 years ago that this was finally done, but they have done it, and it's beautiful and it works. So here we go. We've got particles acting like waves. Except that if you look in more detail at what happens in the experiment, what you see is not something that looks like waves at all. You see that these individual points are individual electrons being detected. So every time you get an electron detection, it looks like a localized particle. But then as you start to detect more and more electrons, instead of looking random, you start to see a pattern emerging. The more and more electrons are coming in now, and you're beginning to see how this interference pattern builds up. So you can see that there are brighter areas where you've detected more electrons and darker areas with fewer electrons. And so this starts to build up into something that looks like an interference pattern with these characteristic fringes, except it's not an interference pattern that's made up of some kind of smooth wave interference. It's a pattern that's made up of individual particle-like detection events. So when these electrons are detected, they appear to be localized particles, but the overall pattern shows interference patterns that are characteristic of waves. All right, so something weird is going on here. Clearly, we've got something funky about these electrons. We think they're particles, they look like particles when we detect them, but they have an interference pattern which suggests that there's something going on which is like waves. So that's electrons, and they're definitely particles, right? If we do this with waves, it's not going to look like that, is it? Well, or is it? Because some other very clever experimentalists a few years later went and did this experiment with single photons. So these are single quantum particles of light. And they've done a double slit experiment with particles of light. And what you see is that actually you have individual detection events happening here as well. And like the electrons, those individual detections build up over time into the interference pattern that's characteristic of waves, as we would expect from light. So we were so sure from this interference pattern we'd seen that light was a wave, but now we see that light also behaves like particles. And we've got particles that are acting like waves. So we are forced by the experimental evidence into this idea of wave-particle duality, where particles act like waves and waves act like particles. So what do we do with this? This is weird. How do we describe this in a way that makes sense, that allows us to make predictions about what we see in experiments and to explain what we're seeing there? This idea of wave-particle duality means that we actually need a new mathematical description for quantum things. Instead of the classical trajectory of the classical wave function, we have something called a quantum wave function. And the quantum wave function is found by solving the Schrödinger equation, which in one dimension looks like this. And this looks a little bit daunting, but it's actually relatively simple. We have, first of all, a kinetic energy term, and then we have a potential energy term. And on the other side, we have something that tells us how the wave function changes in time. The solutions to the Schrödinger equation tell us what types of wave functions are allowed for quantum objects and how those wave functions behave in time. Okay, the Schrödinger equation is a type of wave equation. It's not the same as a classical wave equation. Unlike a classical wave function, a quantum wave function is allowed to be complex. This is a problem because we can't actually measure imaginary values in the lab. We only ever actually measure real quantities. What's more, as we've seen from the experimental videos that I showed you, when we detect something like an electron or a photon, it appears to be a particle, which means we only ever see it at one location in space. So what is waving here? What does this wave function actually mean? If that wave function can't be physically measured, then how do we interpret it? And the typical way that we do this is through the Born rule, which is a postulate of quantum mechanics. It's something that was introduced to try to explain the observations from experiments and to develop a consistent mathematical description. And this says that the wave function, or rather its absolute value squared, defines a probability distribution for the location of the particle, which means that we have a probability of finding a particle between x and x plus dx at some time t, which is given by the wave function times its complex conjugate. And this is what gives us the particle-like properties of a quantum object. It doesn't come from the Schrödinger equation itself. We have to have an additional postulate to explain that behavior. And in fact, although a lot is said about quantum weirdness, almost all of what we consider weird about quantum physics comes directly from these two equations. It comes out of the mathematics. There's the Schrödinger equation together with the Born rule, and this gives us a very precise description of what we see in experiments. The problem is that although these are perfectly mathematically sensible and consistent, when we try to interpret that mathematics using our lived experience in the world, things start to seem very strange indeed, even paradoxical. The uncertainty principle has made its way into a lot of popular understanding, a lot of popular culture. So this is a quote from Terry Pratchett's novel, The Fifth Element. And he's got Death, who has heard of the uncertainty principle and is now turning up only when people are possibly going to die rather than absolutely going to die. And this is actually quite a common conception of quantum physics, is that the uncertainty principle means that we're not sure about anything anymore. And in fact, that's very much not what it means. The uncertainty principle itself can be seen as a consequence of wave-particle duality, particularly about the wave side of that. If we have a wave that has a well-defined wavelength, it's a single wavelength, it's just a sine wave, it actually, although my picture doesn't, the wave itself continues on forever in space. So we can't actually say that that wave is localized in one position in space. It kind of spreads over all of space. If we want to get something which is more localized, if we're talking about waves, then we have to add up a bunch of different waves that have different wavelengths. And as we do that, we create what's known as a wave packet. And this has some localization in space, but the expense of that is that we no longer have a well-defined wavelength for that wave. And we could put that together with another postulate, which was made to explain experiments by de Broglie, which is the relationship between momentum and wavelength. And they're related via Planck's constant h. So we can relate uncertainty in wavelength to an uncertainty in momentum. And from that, we get the canonical uncertainty relationship, which says that the uncertainty in position times the uncertainty in the momentum is greater than or equal to h bar over 2. So h bar is just equal to Planck's constant divided by 2 pi. So this is actually a very natural thing for waves. The one thing that we've had to add here is the relationship between wavelength and momentum for a particle. When we start talking about particle properties, the uncertainty that we have here is to do with the statistical variation that we get when we make measurements of the position and when we make measurements of the momentum. So actually, this is quite a precise statement about the statistics of measurements which we make kind of simultaneously. So it says that, in essence, the better we know the position of the particle, the less we know about the momentum of that particle. And specifically, there's a minimum value for the product of the statistical uncertainties in those measurements. So this is not saying that we're not certain about anything. It is making a mathematically precise statement about the limit on how certain we can be about a particular set of measurements. Another thing that often sounds mysterious is the idea that you can have a particle that's in two places at once. And this is known as the superposition principle. Mathematically, this is perfectly sensible and well defined. The sum of two solutions to the Schrödinger equation is also a solution. That's quite a general property of certain types of differential equations. And actually, that makes a lot of sense as long as you think about waves. There's no reason we can't consider a wave to be in more than one place at the same time. And we can take two different waves and add them up and find interesting results. We get this interference pattern between them. So as long as we're thinking about waves, superposition makes sense. It only gets weird when we start thinking about superpositions of the positions of particles, or superpositions of live and dead cats. But this is really a consequence of our intuition and thinking about particles as being fundamentally localized objects, where we should be thinking about them as having wave properties as well as particle properties. Somehow we have to get from this description of a wave function to something that acts like a particle. We've seen in the experiments, if we believe that properties of this quantum object are somehow described by this wave function that follows Schrödinger's equation, and then at the end, when we actually measure that quantum thing, it looks localized like a particle. So something is clearly happening in between in this measurement process, which is taking us from the wave function that describes probabilities to something that always looks localized like a particle. That wave function doesn't tell us exactly what the outcome of a measurement, the position of that particle will be, but it does give very precisely the probability that we will get a given result when we make a measurement. So again, it's not saying that everything is uncertain now, that we don't know anything about this particle. We do know a lot about this particle. We know very precisely the probability that we will find it in a given place. We just don't know what in the individual particle is going to do when we measure it. However, after we make that measurement, if we then immediately repeat it, we will get the same result, which means that we do know something definite about the position of that particle now. So there's been a change from the original wave function, which gave us a spread of probabilities, to now, after we make the measurement, we have a definite value for that position. And this is what we term the wave function collapse. So we've taken this wave function, which was kind of spreading out over space, giving us a distribution of probabilities, and it's now collapsed down to a wave function which is centered on a particular position. That then serves as the initial condition for further time evolution. So that will then start to spread out in time. Okay, so quantum locked weeping angels. Does anybody believe that? Are they just throwing out the word quantum because it makes everything sound sexier? Interestingly, this is one point where science fiction had kind of got it right. And this is a consequence of the collapse of the wave function in the context of measurement. So this is a real effect. It's something called the quantum Zeno effect. And what it says is that if you keep measuring something very quickly, those repeated measurements keep giving you back the same result. So effectively, it freezes the quantum evolution of that state. So if you measure the state of a particle or a weeping angel frequently enough, it actually gets stuck and it can't move. So this is not quite as exciting a plot as the weeping angels, but what this shows is actual experimental data. So where you have normal time evolution of an unstable state, and then if you measure it frequently, then you can see this slowdown of that decay. And if you do this frequently enough and precisely enough, you expect that that decaying particle is going to get stuck here in that same state. However, and this should perhaps worry you, there is also an anti-Zeno effect, which means that measurements can actually have the opposite result and speed up the evolution. And you're dead. So we see that quantum mechanics only predicts the probabilities of measurement outcomes. And once we've made a measurement, we do know something for sure. But what happened before that measurement was made? And this is where we get different interpretations of quantum mechanics. There's a realist interpretation, which says, well, don't be silly, a cat can't be alive or dead. It can't be alive and dead. It has to be either alive or dead. It must have been alive or dead before you actually observed it. Particle had to be really there. Quantum mechanics must be incomplete somehow if it doesn't give us that information. Or there's the Copenhagen interpretation, which says, well, the particle wasn't really anywhere. Measurement collapses the wave function. That's the only point at which we can actually ascribe a particular position to the particle. Another option is many worlds, which essentially says everything happens somewhere in some universe. And then finally, we have the favorite of many physicists, the agnostic approach, which just says it works, shut up and calculate. But one of my heroes in physics is John Bell, who back in 1964 took this philosophical debate about the meaning of quantum mechanics, the interpretation of the wave function, what happened before the measurement, and he turned that into a mathematical statement that allowed experimental tests to be carried out to test whether the realist or the Copenhagen view was correct. And there's been many experiments following on, all of them trying to successively fill possible loopholes in the theory, but all of those experiments support the Copenhagen interpretation. And they say that either the notion of locality or the notion of realism, which means the existence of some property prior to a measurement, has to be abandoned. Okay, so in the last 5 minutes or so, I want to switch over and talk a little bit about bringing quantum mechanics more into the everyday and relating it to what we see. So this is a really very successful and well-tested theory. It explains why atoms don't collapse. It explains why the sun shines, even though it's far too cold to do so. But from the very early days of quantum mechanics, physicists have been very much puzzled by why things behave so differently on the small scale and how they get from that weird quantum behavior to the classical behavior that we see all around us. How do we get from that weirdness to normal, everyday classical behavior? And early on, people thought that it was really to do with size. So the much abused correspondence principle, which is due originally to Bohr, suggests that for large quantum numbers or large numbers of particles, large masses, things like that, large energies, then we should recover classical physics. So then the question becomes, how big is big enough? Where do you set that boundary between quantum mechanics and classical mechanics in some kind of size scale? This is another one of those questions that you should be wary of asking experimentalists, because they're going to take that and run with it. So how big can you go? So here's one: quantum interference with buckyballs, carbon-60 molecules. So there have been some very clever experiments carried out. So this is what you see. Effectively, this is putting the buckyballs through a single slit, so when we're not interfering them. And then if you put them through a diffraction grating, equivalent to having two slits open, then what you see is a very different pattern, which shows characteristic interference fringes. So this is not something that happens only at the scale of electrons. This is something that can happen at the scale of a molecule made up of 60 carbon atoms. And of course, that's carbon 12, carbon 13, could be a little bit. So actually, there's a lot of individual particles, electrons, protons, neutrons that go into making up these molecules. And you can still see quantum interference. So, okay, that's pretty impressive. But they didn't stop there. So here's some more experiments where they started with, this is the original buckyball. And they've started going to bigger and bigger engineered molecules. So these are large organic molecules. You can see this is a scale bar for about a nanometer. So these are getting into things which are several nanometers in size. They're not huge yet. We're not to the scale of cats, but they're certainly not an electron either. And they don't even stop there. They're keeping on going. So this one is an antibiotic polypeptide. It's a naturally produced biomolecule. They've been thinking about experiments with deactivated viruses. And it turns out, lo and behold, you can still see quantum interference effects, even with molecules of this kind of size and complexity. So, okay, can you go any bigger? People over the last 20 years or so have started developing devices which are nanomechanical or micromechanical resonators. So these are things like tiny guitar strings. So this structure here is built out of silicon nitride with a bit of gold on top. And it's actually free to move in the plane here. That changes the capacitance with a gate here and here. And so you can actually detect the motion of this mechanical resonator. It's very much like a tiny guitar string. We've got a 2 micron scale bar. So now we've gone from nanometers to micrometers. So up by another factor of 1,000. And there are different geometries. So this is one that behaves like a drum head and is getting to an even larger kind of size scale. And this one is a cantilever, quite similar to a diving board, in fact. And you see the scale bar here, this is about 60 microns long. And all of these devices have been shown to be operating down into the quantum regime. So as my PhD supervisor was fond of putting it, this is putting the mechanics back into quantum mechanics, because these are literal mechanical resonators. So we're still a long way away from the scale of cats, but nevertheless, we are a very long way away from the scale of electrons. And we're learning things with all of these experiments. You've probably seen a lot these days about quantum technology, the revolution of that. We've got IBM's quantum computers, which you can actually go and run programs on. They are cloud accessible. You can sign up for a free account and you can actually run code on a quantum processor. Something that I've done with some of my undergraduate project students. There are now beginning to be commercial quantum sensors available. There's quantum key distribution, which is one of the early technologies, and in fact, something that I worked on when I was about your age with a summer internship at the Los National Lab. And these are all now commercial technologies that are available. People are making money out of these things. But there's an elephant in the room. The thing that makes all of these technologies very difficult and very challenging is something called decoherence. It turns out that in the real world, quantum systems are never actually isolated. They interact with their environment. And all of that quantum weirdness is actually very fragile to noise. So it's not just the size of something that matters, it's its temperature. So how cold can you make it? Because that will reduce the thermal noise. It is isolation from vibrations, isolation from stereoelectromagnetic fields, isolation from cosmic rays coming from space. And it is really the decoherence and the noise that is the primary challenge for quantum technologies. And when I say a huge challenge, I mean literally a huge challenge. So all of this kit in here is the kind of equipment that you need in order to cool quantum bits that are used for quantum computers, for instance, down to just a few fractions of a Kelvin above absolute zero. And it takes that to actually isolate them sufficiently from the thermal noise, from the environmental noise, in order to be able to measure their quantum behavior. So when I was a PhD student, I was working with an experimental group who were doing nanomechanical resonators. And their experiment was in a big refrigerator like this, a dilution refrigerator. That dilution refrigerator was hung off of an optical bench, which is about probably 30, 40 centimeters thick. It's got huge legs on it for vibrational isolation. And that was up above head height. So the dilution fridge was hanging off of it. The entire thing was contained within a copper room, which is a Faraday cage for isolating it from electromagnetic radiation. And even then, these are incredibly difficult experiments to show the quantum behavior of these still very tiny objects. They're getting close to being visible with a light microscope, but they're still very small. So actually, the conversation these days is less about what is the size at which things become classical rather than quantum. But we're understanding now that it's not just size that matters, but it's really how well you can measure something and how well you can isolate the quantum effects that you're interested in from their environment. So this is one way that we now understand the classical world emerges from the quantum mechanical. But actually, that's still quite an open question. And it's one of the things that I'm working on. It's one of the things that quite a number of other people are working on, is how do you recover that classical behavior from all of this quantum weirdness? So this is the end of my story for today. possibly just the beginning for you. Quantum mechanics, in a mathematical sense, is a phenomenally successful physical theory. It's given us unprecedentedly precise predictions for many experimental quantities that we've measured. And so far as we understand, it works beautifully. But that mathematics describes a world that's very different to the classical world we experience in many weird and wonderful ways. And I think that's a lot of the appeal of quantum physics. It certainly is for me, this counterintuitive, brain-stretching concept of it. And with the rise of quantum technologies, learning how to harness that weirdness to do useful things is actually teaching us a lot more about how to understand those fundamental ideas of quantum physics. It's been perhaps a quiet revolution in the interpretation, the understanding of the fundamentals of quantum physics, but it is a revolution nonetheless, and it's really changing the way that we think about it. But there's still very much to be explored and discovered in the realm of quantum mechanics, and I hope that some of you might be interested in doing some of that yourself.